Today we would like to conclude a lecture on this course. We started as mass transfer 2 in the first lecture. Alright, and if you recall, we said this course is about separation processes. So we classified different processes as subgroup of unit operations. Alright, and then we said that for this course we have in the syllabus absorption, distillation, extraction, adsorption, and drying. So these are the 5 different unit operations for this course. Alright, what we do today, we would like to summarize, and we would like to see how, based on our knowledge of different unit operations, our approach starting with thermodynamics, then the rate processes, then some certain numericals or examples, we can address similar other unit operations or the same unit operations with slightly more complexities. Alright, so first we said that we have to have a very basic knowledge of diffusion. That's a very basic ingredient of mass transfer. So in that respect, we had a discussion on mass transfer coefficient, different theories, film theory, surface renewal theory, boundary layer theories. Okay, so these are the 3 main theories. So we had a discussion on how to calculate the rate. So we developed a rate expression in terms of mass transfer coefficient and driving force for diffusion in terms of concentration gradient or in terms of partial pressure. Alright, so once we had this rate expressions, then we said that we have to start with thermodynamics or the equilibrium. So when we have the equilibrium, either in case of absorption or distillation or adsorptions, then we say the rate is 0. So we talked about the interface. At the interface, 2 different streams, there is no rate. In other words, mass transfer rate expression Km into del C, driving force is 0. So then we had those thermodynamic equilibrium curve, solubility curve established from the experimental or from certain handouts. We had isotherms for adsorptions. Alright, for extraction we said that we need a data on immiscibility or the miscibility, solubility of 2 different liquids. So once we have the thermodynamics, then we said that we need to have the approach. So there are 2 approaches. One was a rate based approach, one was a stage wise or equilibrium wise. So in principle, one can apply any of the 2 approaches to address any unit operations. But if you have some unit operation which has trays or stages or cascades, then it makes more sense when we can apply this equilibrium wise approaches. So we said that 2 living streams, they have enough resistance time, they mix with each other and they live in equilibrium, and that coordinate of the 2 streams, they fall on this equilibrium curve. When we have the rate wide approach, then we need to have a more rigorous approach. We need to write down the differential balance, species balance, then we need to integrate the system. And in that respect, we said that the approach of NTU or STU makes sense here. That's more of an approximation, but still one can design the column or the unit operation which is dealing with. So essentially we have 2 approach. One is the equilibrium wise approach, stage wise, and the other is a rate wise approach, in which we have this NTU or STU approach, simplified version. Then we talked of operating lines and the equilibrium lines, and then the stages, etc. In that also we said that of course we are discussing about mass transfer, but hydrodynamics also plays a major role there. So very often when you have this counter current system, gas, liquid, or even if you have the solid and the liquid or gas flows through it, then we have to worry about, or we have to be concerned about pressure drop or fluidizations or loading and flooding. So these are the 3 major ingredients of hydrodynamic discussions, and very often it happens that one has to do iterations. In other words, if mass transfer says that we have so much of diameter, the length of this column, then one has to go back and check from the hydrodynamics whether we have a reasonable pressure drop, because that will decide the cost of the power, cost of the pump. So we have the economy also, cost also. Safety issues, disposal issues, these are the other issues which if you have any course on design, then you will be dealing with all kinds of aspects, mass transfer, hydrodynamics, cost, economy, and the safety issues. Okay. So the way we will conclude today's lecture is we will sum up the way we started this course in the main approach, and then we will take one very simple example where we have such certain more complex system, how we can address this based on whatever knowledge we have. Right. So of course we had only 5 unit operations, but you can have some new type of unit operation which is not included in this course, but still by the same approach we can address that type of problem. Okay, so let's sum up so far what we have done in this course as far as approach is concerned. So we started this course as mass transfer 2. Okay, we said it's about separation processes, and we said that we can classify different processes from the operation point of view as unit operations. Alright, and for this course we said we are going to have discussion on absorption, then we switch to distillation plus say gas or air. Alright, so we have multi-phase, at least two phase systems we have, and we have generally one component, or we can have multi components. So we are talking of transferring species. So we have transferring species which diffuses from one phase to another phase. Okay, so when we took up this unit operation one by one, before that we had 1 or 2 lectures on basic or fundamentals of mass transfer. Alright, so in this, if you recall, we started with diffusion. So we said Fick's law, flux is given by minus T into concentration gradient. Then based on the diffusion, we talked about different theories. We introduced a parameter, very important parameter, mass transfer coefficient. Alright, so based on this definition of mass transfer coefficient, we talked about the flux rate. So at what rate certain species or transferring species is getting transferred from one phase to another phase. So this meter square is the interface area, and we said that by invoking this parameter mass transfer coefficient, we can have driving force or mass transfer from one phase to another, and we can write in several ways: Km, del y, Kp, del p, etc. Alright, so this is about the rate one has to measure in terms of mass transfer coefficients, and all these mass transfer coefficients Km, Ky or Kp, they were shown to be a function of Reynolds number, Smith number, etc. So different theories like film theory, three most popular theory: film theory, we have boundary layer theory, we had surface renewal theory. All this theory ultimately gives us an expression for mass transfer coefficient in terms of operating parameters or the physical property of the system. Then once we had the definition for mass transfer coefficient, we talked about two-phase film theory. So now we are talking of an interface of two different phases, liquid and gas, and then we said we can have two resistances where we have this concentration drop like this. So instead of working on individual film transfer coefficients, we said that we can also write the expressions for flux in terms of overall mass transfer coefficient and two concentration in the bulk phase. So Y star here would be in equilibrium with, let's say, with X1 on the other side. Alright, so essentially we have this engineering parameters to estimate this rate. After this, we talked about what is the step here, right? Our approach. The first step here is equilibrium. One has to establish an equilibrium. Okay, one has to do the experimental, or one has to do some experiment to generate these data for solubility or for isotherms or for solubility of one liquid into another liquid, or one has to rely on literature surveys or literature values. Okay, so the step one, if you want to write down, a very common step for all unit operation is about equilibrium, at which rate is 0. Okay, And then if you talk of absorption, we have solubility curve. So given partial pressure, what is the concentration? Given partial pressure, what is the concentrations? Okay, so this is about, say, sulfur dioxide, about ammonia, all right, about H2S in gas phase, and how much is the concentration, say, milligram per liter in other phase. Then we came to the second unit operations, which were distillations. So here also we have different mechanism, but we have the same approach, that one has to establish a relation between mole fraction in one phase to mole fraction in second phase. So we have this Rawls law, which gave us y versus x. Here also we can write C versus partial pressure in terms of y versus x or x versus y here. So idea is that step 1, we have to generate such kind of data from the experiment or from some literature values. We came to the third unit operation, which was extraction. What we have here, we also have a phase diagram. So we said, so percentage amount of solvent S, and here we can have x and y as in extract phase and the raffinate phase. We need to know what is the equilibrium concentrations. So they connect here between this, between this. So this is also about y versus x in two phases, extract and raffinate. Okay, then we talked of Langmuir isotherms. Given partial pressure in one phase, what is loading Q milligram per gram. So given partial pressure in the gas phase, how much CO2 or sulfur dioxide will be absorbed to give this loading. Or even in the aqueous phase, we can say that C aqueous, given so much of concentrations, how much is the loading of fluoride or arsenic on certain materials. So these are the 4 unit operations where we talked about this equilibrium form thermodynamics. We also had drying, the last unit operations. There also we have a very similar curve like this. Moisture content in equilibrium as a function of saturation humidity or relative humidity, relative saturation. So partial pressure of the gas, non-dimensionalized with respect to the partial pressure of liquid or water in case moisture, pure moisture at a certain temperature. So here we said we have different region for a given quality of this air, moisture in a certain solid cannot go below this. So this is your x star. So here we had this unbound moisture and the bound moisture, etc. All right. So our idea here is that irrespective of the unit operation, one has to start with the equilibrium. You have to establish, given activity in one phase, how much is the concentration in other phase, or the vice versa. That's equilibrium thermodynamics. Once we have established thermodynamics, then comes your rate, and which we already addressed. Rate can be written in terms of mass transfer coefficient and the driving force. Okay, but then we said that now about 2 different methods or 2 different approaches. In one approach we have equilibrium stages and the stage wise approach, and the second is a rate wise approach. Okay, so let's see, let's note down this also, that in step 2 now, once we have thermodynamics, now we are talking of 2 different methods or 2 different approaches. So what approaches we have? We have equilibrium approach, right, or we say stage based approach. And the second is your rate based approach. Okay. Now before, these are the approaches, we must not forget that a real system, or from the operation point of view, we have a different type of arrangements. So now we are talking of contacts. All right. So we can bring 2 phases in contact in stages, or we call it cascades, or we call it trace. All right. Or we can have continuous contact. So essentially here very often we talked of packed bed, for example packed bed. Now again try to understand this and try to recall that our approach are different and the real process is different, right? In principle one can apply any of the two approaches in any of those whatever we have, but for our convenience, if we have trays like in distillation column, one would like to apply this equilibrium based approach. If you have a continuous packed bed like a packing, or you have absorptions, right, one should apply in principle rate based approach. For simplicity, of course, one can always have concept of theoretical stages, theoretical plates, height or distance between the two plates. One can do this, right? But for our convenience, if you see the real system in which we have the trays, we can think of equilibrium approaches. Two living streams are in equilibrium. So when we talk of say distillation, we say that we have trays, so we can apply equilibrium approach. The vapor which leaves and the liquid which leaves, they are in equilibrium. Their coordinates are given in the approach 1 when we had this relative volatility y versus x. So this gives us y versus x. Alright, so that's the distillations. When we talked of extraction, then we say that well we have cascades. So one is streams, another is streams, give them equilibrium, they leave in equilibrium. So here also you bring this constant raffinate in case of extractions, treat with the solvent, we have extract here. The two living streams are in equilibrium, and these two living streams one can mark on this equilateral phase diagram as a tie lines. So here we have y and here we have x. So we are talking of equilibrium approach or a stage wise approach applied to stage wise operation. Like in distillation column, in extraction column. Adsorption also we had one example where we had this type of system where the liquid was brought in contact with the solid and then taken to the second stage or more than that. Okay. When we say rate wise approach, then here we are talking of continuous packed bed column. Say we can have the liquid and we can have the gas flowing in the counter current operations like in absorptions. Alright, let's talk of adsorption, that also we did. So we have fixed packed bed and certain gas contaminated with certain species is brought in contact and it treated stream leaves from one end. So this is adsorption. These are all continuous contact wise process. Here we don't have stages like this, which means things like this or operations like this, we are talking of rate at a finite rate. From one stream to another, one phase to another phase, we have finite mass transfer, n equal to minus k y minus y star, some kind of definition for mass transfer coefficient. So in principle one has to write a very rigorous species balance for this. Here we don't get into details of interfacial mass transfer or the time over which this stream is getting mixed with this stream and there is a mass transfer. It's more like a steady state process. After time t, the two streams have been given enough time to mix and transfer the maximum species from one phase to another phase. Similarly here distillations, at every tray of the distillation there is a pool of the liquid, so that when the vapor comes in and the liquid drops in, there is a mass transfer, there is a rate, but overall our approach is that two living streams where they have spent good amount of time here, so they are in equilibrium. So we don't get into this rate based approach. Here we have the approach, since the process is continuous, here we have the rate wise approach, in which case we wrote down generally we have a very comprehensive species balance of this order. Species is brought in and out by convection, species is brought in and out by dispersion or by diffusion, and then we have rate at which mass is transferred from one phase to another phase. Okay, then this has to be, in principle this has to be solved by certain initial condition and certain boundary conditions. Alright, but here we said that instead of solving this compressive equations, this differential equations, there's an approach of NTU and STU. So if you recall, we did make some species balance, we had simplifications, then we invoke the concept of number of transfer unit and height of transfer unit. This approach can be applied in absorption. We can also apply in adsorptions. So there also it's possible to apply this type of approach. We can also apply in case of drying, although we did not invoke this NTU and STU, but you look at some of the textbook, they do have this type of approach. Drying also, when you have the solids, a packed bed of solids, say grains, wheat, which you want to dry of moisture for its longevity, you bring in contact with the hot air. So you're very similar to what you have in case of adsorptions. You have the similar situation here. The moisture is driven off from the surface into this air. So here also one can apply the concept of NTU and STU. Okay, we said that NTU, very common definition we should remember, is nothing but dy over y minus yi, but we should look at fundamentally that is nothing but difference of whatever is the enrichment over the average driving force per mass transfer. Alright, so you bring this NTU, number of transfer unit, you are saying that this packed column is if there are certain physical or hypothetical, there are NTUs, number of transfer unit. Each transfer unit has certain height, which is a function of mass transfer coefficient, and AS, some surface area per gram. Unlike, you go back to the previous slide where we talked of this stage-wise approach. Here there is no Km. Alright, we make overall balance between one stream and another stream here. So here we have this different trays. Alright, in case of drying, it's also possible that we have the trays like this. So in principle, we can also make an approach here. We can also have an approach of trays-wise approach here. Similarly, instead of NTU and STU, if you look at some of the old textbook, they also talk about NTP, number of theoretical plates, height equivalent of a theoretical plates. So it's a very old approach. The idea what we are trying to say here, that if you have a continuous packed bed, continuous contactor, one has to write down most fundamentally, most basic, a species balance, then one has to integrate. But since because of to avoid these mathematical complexities, we have these quantities like NTUs and STUs. One can also say that, well, this column is equivalent to certain trays where you can apply the concept of NTP or HTP. So it's a different approach. Okay. So for different unit operations, absorptions, we worked on NTU, STU. For distillation, we talked in terms of trays, real trays, as well as our theoretical trays. Okay. Of course, we had this equilibrium and non-equilibrium conditions, etc. In case of adsorptions, we talked about this breakthrough curve. How do we get the breakthrough curve? We write down the species balance, differential balance, and then we solve with a certain initial and boundary condition. Drying, we can have both trays wise, we can have a continuous dryer. We gave an example to remove moisture from the grain. So there one has to write down again differential balance, one can integrate, one can also invoke the conditions, invoke these parameters like NTU and STU. Extraction, liquid extraction, we talked about two liquids brought in contact in a stage, in a mixer, then we have settler. So we said the two living streams are in equilibrium, rate is 0, maximum mass transfer, we have how many stages. We can also have a real industrial extraction column where the two liquids, they flow in opposite directions through some contactors. There one can also bring these parameters of NTU or STU, one can work on this. One can also take the very other approach in terms of number of stages. Okay, so these are the two approaches, you must not mix with it, they are separate. Real unit operation is separate. In principle, one can apply one to any of the two different ways of contacts. Okay, idea here is that after deciding that what approach we have to, we need to have an equilibrium curve and we need to have an operating curve. That's what we did in case of distillations, right? We had the number of trays, we made a species balance. Extractions, we had the operating line and we had the tie lines. So whenever you have the equilibrium stage-wise approach, the one very common approach is that you identify your two coordinates which are on equilibrium given by the tie line, and the two coordinates which are on operating lines, not in equilibrium. So there is a finite mass transfer. Okay, so we would like to just sum up what we said here about this species balance. So in general, if you have a two-phase system, so when you have the trace-wise approach or stages, or you have cascades, okay, then first is we're talking of two phases with two different concentrations or mode fractions. So we have y versus x given by this operating line. So this is the most common approach we had for distillations, we had for extractions, we also did for adsorption. Whenever we have the stages or cascades, you need to write down, you need to have an operating line. So what is operating line? You need the connections, or you need some expressions which connects bulk phase concentration in one phase to another phase. Essentially, you're talking of material balance or a species balance between the two phases. And then you have on top of this y versus x star given by this equilibrium line. Alright, so if you go back, we talked about distillation column. We take certain states in here. We have the vapor, which is a concentration yn, liquid leaving that trace xn, the vapor which arrives as a mole fraction yn plus 1, and the liquid which arrives this stage is xn minus 1. So we need to have a material balance so that we have an expressions between yn plus 1 versus xn. And we have the tie line given by the equilibrium curve where we have yn versus xn. So with this we develop this Machiavellian methods. So now we are talking of thermodynamics on which we have superimposed our material balance. So this is thermodynamics on which we have superimposed our material balance. So we had this operating line 1 and we had operating line 2. So what it does for a given mole fraction x, if you go to the operating line, if this is xn, this will give you yn plus 1, and for the same xn, here you have yn star, or vice versa. We talk of this Ponchon-Severett methods instead of Machiavellian methods. We have the enthalpy curve for HV and we have HL. So again we located a differential point del, so that we say that if we have yn plus 1 here, if you connect this, this will give us xn. Xn on the other hand is in equilibrium with yn. So yn versus xn by tie line and yn plus 1 versus xn given by this operating line. So what is the operating line? Nothing but this mass balance or species balance. Alright. So these are all steady state process. Now let's look at certain other process like adsorption, drying. Okay. Try to compare this with distillation or with, let's say, we have absorption. Okay. So one thing is, of course, we can always discuss in terms of distillation, which is in trace. Absorption we have in continuous packed bed. Okay, mostly. Adsorption we have a packed bed, two streams, solid phase and the gas or liquid phase. Drying again we have the solid phase and then we have the gas phase. So there is a similarity and there is a contradiction between the two phases. All right, two processes. The another difference which you should notice is about steady state and unsteady state. Okay. So when we say absorption or distillations, we say continuously feed is fed here. We are withdrawing one bottom products and one top product and one is the bottom product. When we talk of absorption, we say that gas continuously is fed in, leaves from here, fresh or some effluent fresh liquid gets in, and treated liquids lift from here, maybe it's get regenerated, and we have this continuous process. when we had this adsorption packed bed, then we talk in terms of how long will it take for the bed to be adsorbed. When we talk of drying, we say that how long will it take for this solid to be removed from this moisture. So you see the difference here, that certain unit operations we are talking in terms of steady state. Alright, we are not interested in a startup, which you will do in different course like process control. Alright, here we are talking in terms of unsteady state. How long will it take? Okay, so let's again try to understand the difference between these unit operations. One is, of course, we said about stage wise and contact wise. That's one thing. Approach, NTU, STO, or equilibrium stages. Okay, that's another way of classifications. Now we are talking of steady state and unsteady state. Why certain processes inherently we treat them as unsteady state, right? We said that adsorptions. So we bring in some contaminated gas which we want to remove, SO2 from air. We bring in contact with zeolites. So zeolite has a finite capacity. Once it gets saturated, adsorbed, one has to regenerate it. Okay. In case of absorption, mind you, we say that continuous, but you must not forget that the liquid or the spent liquor, which is also saturated, has to be regenerated in the second column and has to be brought back. Okay, so there also we have the similar situations, that certain phase is getting saturated, except that the way we treat, we say that is a continuous process because we have the parallel second stream. In case of adsorption, what happens? Or drying, we have trays, stacks of solids which we have to dry from one moisture level to another moisture level. So we bring in contact with certain air, it gets dried, stop the things, bring in the fresh one. We can also have a continuous process for adsorption and drying. What will be the constraint, or why we don't have so commonly? Because now we are talking of handling of solids. A solid falling from a height will break, right? So there's the breakage of the solids. We don't have this kind of operational difficulty in case of liquid and vapor. So we have a very continuous process. Continuously you can bring one phase, continuously you can remove the second phase. In case of solids, we cannot think of stages where from one stage solids will fall into the second stage and etc. You may see certain dryers with that type of arrangement trying to make the process continuous, but there is always very huge risk of solids getting broken into several pieces, and then blocking or choking occurs. One has to stop it. So now you should see the difference, that why a process is treated as steady state, why another unsteady state, because of the operation difficulties. In principle, we can have adsorptions. Say we talked of the PSA system, pressure swing adsorption. Okay, so pressure swing adsorption. In the previous class on adsorption, we had a very brief introduction on this. So now if you have one bed of the solids and we bring air which we want containing, say, carbon dioxide in nitrogen, and treat this here, now this concentration of CO2 will be very small here, but slowly and slowly this bed will get saturated, this concentration will pick up, and now we have this breakthrough curve. How do we make this process continuous? Well, one has to bring this second adsorb, so that when this is adsorbed, then you can switch to the second bed, and during that time one can regenerate this place. So here a process which is inherently unsteady state, from the operation point of view we are saying that this can also be treated as a continuous or a steady state process, because here the concentration or the purity of the stream which is leaving is made deliberately constant by continuously switching from one bed to another bed. In industrially, we look at, at a higher graduate level, you have something called SMB, simulated moving bed. Alright, here by sequencing, by changing the sequence, by taking more number of beds, one can have a solid phase which is a stationary behave like a moving bed. So we are talking in now PI, process intensification. So these are certain advanced topics which you will meet across at the graduate levels. Okay, so the idea here is, again, for the discussion, that whether it's a steady state or unsteady state. In the industries, to begin with, yes, plant is under startup, whether it's a distillation column or adsorptions. So a cold plant which is not used for a long time, or say the power has gone off, power is off, plant is shut down. When you start, there is a time, unsteady state. That's one thing. Once the process reaches a steady state, then we have a continuously purity maintained, continuously concentration maintained. Okay. Certain process like adsorptions, drying, where we have mostly solids. If you have the solids, then also we can have continuous process, like in SMB or 2 beds PSA system. Okay, we can have that, but it's a question of difficulty in the handling of the solids, which has to flow by some other techniques. Fluidizations can make solid flow from one trace to another trace. It's possible. Okay, but we must understand that each process there is a similar, each unit operation there is a similarity, there is a difference, either in terms of mechanism or in terms of operations. One has to have the approach clear that first we need to have an equilibrium, then we need to have operating line or a species balance, then we can address how many trays are required given the flow rates, etc. There's another thing here about hydrodynamics. So in this course we had discussion on mass transfer, or we dealt with mass transfer aspects, but there is also very important consideration of hydrodynamics. In other words, if you have a packed bed of solids and you allow gas and water to flow through this, one has to be considerate about pressure drop, because that will decide the cost of the power, cost of the pump. Or at high flow rates or relatively higher flow rates, there is a possibility of solid beds getting fluidized. Once the bed gets fluidized, then there is a risk of carryover also. Alright, in some cases we do require fluidizations for high heat transfer coefficient or for high large mass transfer coefficients. Okay, if you have a continuous packed bed, say absorption, gas flowing in one direction, liquid flowing from the other directions, then we talked about loading and flooding. It's possible that at relatively larger liquid flow rates, that liquid will prevent gas, that liquid which is flowing from the top will prevent gas to flow from this. So there will be a flooding of the column with the liquid, or entire column can be loaded with the gas. So we have that type of constraint. Similarly, one has to worry about the pressure drop. How much is the pressure drop in the continuous countercurrent process? Okay. So of course in this course we didn't have much discussion on hydrodynamics. We just had one plot, if you recall, in absorptions about the Sherwood-Eckert plot. So when we talk of this hydrodynamics, essentially we are concerned with the pressure drop, because that decides how much is the power. One has to be considerate about loading and flooding in case of continuous counter process or fluidization. So we have not discussed in detail about this, except when we discuss absorption, then we had this very popular graph given by Eckert or Sherwood, where we talked of this loading and flooding curve, or the different pressure drop y versus x, certain gs over ls, if you recall, and certain other quantities, and we said that there is a flooding limit. One has to operate at 70% of this gas or liquid flow rate. So this was the only small discussion we had hydrodynamics, and you have some other course in chemical engineering where you extensively discuss deal with this pressure drop, okay, in multi-phase system or the single phase system. So the idea is that in parallel to this mass transfer, when you design a unit operation, you have to be considerate of this hydrodynamics and also cost or economy, because in case of say absorption, if you want to increase your liquid flow rates, all right, then the cost of the solvent itself will be larger, or may prevent you from going for the larger flow rate of the liquid. Or one has to think of this, after this absorption you have the spent liquor, so one has to regenerate. All right, so the cost also plays a major role in overall design course, which I am sure you will have at some level next year onward. Okay, one has to also worry about, considerate about this safety issues or disposal. All right, so now we are talking of how or where to spend this spent liquor. Do we have to recover the liquid and bring it back to the column? So there we have this cost effect. or how to or where to dispose it. So all of this is a part of another course on design, which you will have, I'm sure, at next third year or fourth year level. Okay, so idea here is what we are trying to say here, that hydrodynamics and mass transfer, they go hand to hand, right? Very often you design a column, then it's possible that whatever, say for example liquid flow rate or gas flow rate you have got, that prevents you in the from a smooth operations or a safe operations. Maybe the liquid flow rate was so high that you have gone into the region where there is a flooding, or the cost of the liquid is so expensive, it's very costly, expensive liquid, so economy may not permit it. So if you have different some type of special effluent which you want to treat, say S2S, right, or such a mixture of SO2 and S2S, you want to sweeten this natural gas, so you have to develop some different type of solvents, very special solvent, which may not be like water, it's a very expensive thing. So there also one has to look at the cost analysis. So everything get together into overall design of any unit operation which you take, whether it's absorption or distillation or adsorption. What we do now, based on whatever discussion we had so far, we take a very simple example. The idea here is to show that if slightly more complex problem which we have not addressed so far, how we can address based on the knowledge which we had. So the most simple, if you think, you may have liked it, about Machiavellian methods. All right, it's about distillation. We want to determine how many trays we have. Okay, so we had a feed stream, we had the condenser, we had the boiler, and we wrote down this material balance. We had this Y versus X graph, and we did this analysis to find out how many trays we had. Okay, now let's take the same example with slightly more complex. How do we make it more complex? For example, let's say that instead of one feed and two outputs, top product and the bottom product, we have one more side stream. Okay, so now we want to see how we can address this, similar this type of problem which we have not dealt with so far in this lecture, based on whatever we have learned. So we will have the same approach as we started today's lecture. We will have the equilibrium, we will make a material balance. What was the objective of material balance? To mark certain coordinates, and then how we can find the number of trays. Okay, so again here we want to address that, if you come across certain more complex problem, you should be in position to address those starting from this first principle. So we can have multiple feeds or multiple withdrawal. Now most of the textbooks on mass transfer, they do address this. We did not address in this lecture, but we like to see how we can solve this type of problem. So let's say we have a distillation column, we have a feed F, mole fraction ZF, top product we have condenser, so let's say it's total reflux, so we have D top product, and we have this XT, and this goes to the top of the first tray here. So we had this vapor which is V, Y1, so this is Y1 here, and we have this X0 which is a reflux here. So this reflux ratio is R, so this stream is R into D. At any stage here N, we have two streams, so this concentration is Yn plus 1, and this liquid which is trickling from the top is Xn. Similarly we have this last tray NP, this stream is brought here, we have the reboiler, we have the bottom product W and XW, and this vapor phase is sent back to this vapor as V bar, and concentration YNP plus 1. So if we choose any trace here M, we have this vapor phase as Ym, right? Here this is Ym plus 1. We have this Xm minus 1 and Xm. Okay, so to address this, we wrote down the operating balance equations for this and for this. So we took two envelopes. We wrote down the first equations for the top column as Yn plus 1 equals L by V Xn plus D by V Xt, which is also we wrote as R by R plus 1 Xn plus Xt by R plus 1. So what we are trying to say here, that first thing our approach was, let's have first equilibrium curve. So that's the thermodynamics. We started with y versus x. Then we made this species balance. So when we say that we have written the operating equations, essentially this connects your yn plus 1 to xn. So if you look at this nth tray, we have yn plus 1 and we have this xn. So two are given by this equation, and this stream which is coming from here is in equilibrium with the two living stream, or this stream is in equilibrium with this stream. So this is your yn is given related to xn by this equilibrium curve. So we had one operating line, then we had the second operating line, and we had this feed line here, which is xn. So it's Macquarrie methods. We assume equimolar similar to yn plus 1. We can also write yn plus 1. So we have taken another envelope here, right? So yn plus 1 equals L bar V bar xm minus W over V bar xw. Or we can also write as L bar over L bar minus W xm minus W over L bar minus W into xw. So again, this operating line 2, which is given by this, it connects ym plus 1 into xm. So then we had this number of trays. Now what we are saying here, now we have a distillation column similar to the previous one. We have F, we are withdrawing this product, dx0, we have reboiler here, so there's a reflux vapor, and we have this bottom product W and XW, F and XF. Now we are saying that let's assume there is one more side stream. We are withdrawing one more product at certain trays S with the flow rate S and XS. Okay. Now the question is that how many trays we require. So the idea of this taking this example is to show that we should be able to address similar, even if more complex problem than what we did so far in this course by the same approach what we have learned: thermodynamics, equilibrium, and the operating lines, which should connect the two bulk phase concentrations, the liquid and the vapor. So let's see how we address this problem. Now we start. So when you have a problem like this, you must realize that one has to divide this distillation column into more than two regions. In the traditional distillation column, or the one which we discuss in this course, we had one product here and another product here, and there was one feed. So we took one envelope like this and we made this material balance between two streams. We take another envelope here, region 2, where we had this balance between this phase and this phase. Okay, so we got the two operating lines, and one we had this Q line given by when we made a balance between the tray on which the feed enters. So with this 3 we had Macquarrie method, we could find out number of trays. Now what we do here, you must realize that if you take this envelope like this, you have the similarly exactly same situations like this. If you take envelope like this, you have the same situations like this. All it means, now we need 1, 2, and we need to take one more balance like this, another region like this, 3. So we have, for this region, we have the first operating line, which will be same as before, yn plus 1 equal to r over r plus 1 xn plus xd over r plus 1. So this operating line holds good between tray 1 and the trays above S. Okay, because this same as above, this S here. So the situation is same as this second operating line we have for the bottom stripping sections, which is ym plus 1 equal to L bar over L bar minus W xm minus W over L bar minus W and xm. Third, you have this Q line, which will be also be similar to what we had here. intersection of two operating lines gives Q line, or if we know the Q line and know one of the this operating line, we can find the second one. So for this column as well, we have this same Q line, similar equations. Now we need one more equations for this. So we need operating line 4. Now without making material balance, by analogy, you should be able to write down these equations for this operating line between the bottom plate and this top and the top product here, just underneath this S plate, the way we did it here for this nth plate. All right, we should be able to write down by analogy. You can always go back and make, starting from the first principle, that this is a Sth plate, so we have y s plus 1 and we have xs. So take this envelope. Now we have two products, d and s. So what do we get here? We'll write y s plus 1. Now we have r over r plus 1. What was r plus 1? This was L by V. So here we have L and V. Here we have L bar and V bar. So flow rates are constant in Maccabi-Thiele equimolar flow rates. In here again the flow rate will change. Why? Because we have this one more withdrawal. So we have another region here where the flow rate is L1 and V1. That means now we can write just by this analogy that this number is y s plus 1 equal to L1 over V1 xs plus, we have here instead of xt over r plus 1 we had d by v. Alright, so instead of here we had this d by v. So what we should get here by the material balance, dxd plus sxs over v1. You start from the first principle, you should be able to convince yourself that you are getting the same equations here. So what happens to now Maccabi-Thiele plot? Now you have two side streams. Again you start from y versus x. Alright, you have xd top product, you have feed xf, you have the bottom product xw, and now also you have xs. Alright, so now you have four streams, two side streams now, xs and xt, and we have now one feed entry and one withdrawal product xw here. So what you will expect, first operating line which we wrote, it will go from here to here. Second operating line for the bottom product which we wrote like this will go from here to here. So there is a feed here. Feed will give this feed line, Q line. Alright. Beyond this and this, now we have a different operating line. This operating line, what we wrote was y s plus 1 equal to L1 V1 xs plus dxt plus sxs over V1. So it has a different slope and different intercepts. So here now again when you have this xs, you have the second very equivalent to this Q line. Alright. So you must understand that even if we have one feed, we have two product. Now we bring one more product output here. Our approach has not changed. One has to write down one material balance for this, one for this, one for this, so that we have at any trace we have two streams, two incoming streams, and the two leaving streams are in equilibrium, whether you are in this region or in this region. Of course the flow rate here was LV, here we have L bar V bar, and here we have L1 V1. So we had one feed line, one line for xs where we were drawing it, right? If you intersect these two lines, you will get another line here. If you intersect this line and this line, you will get a Q line. So if you know the Q line, this line, you can draw this line. If you know this line and Q line, you can draw the other line. So our approach or understanding of this Maccabi-Thiele method is the same. This is Q line, you can call it this as a S line. Okay. So in this example, again we are trying to re-emphasize that in a course or in the syllabus, if you have slightly more complex problem, given the lecture notes, textbook, one can also approach the similar problems by starting from the first principle. Okay, we like to conclude today's lecture with one more example. If you recall, we said ion exchanges. We talked about this ion exchanges. We didn't have mathematical discussion on this. We said that ion exchanges is very similar to adsorption. All right, what are ion exchanges? In water purification, you use solid reagents. So you have certain molecules, a substrate on which you had some functional groups. So these are functional groups, certain polymeric materials. You want to remove nitrate, say calcium nitrate, sodium nitrate. You want to remove nitrate from wastewater. You bring in contact with this. All you do, you exchange the ions. NO3 goes with R and R dash goes with X. So essentially you have replaced this nitrate, which maybe it was more harmful than the one which you have brought in the wastewater. Now this is a reaction here. Each resin is a solid material. It has pores inside. When you bring in this contact with this, there will be an equilibrium here. So what is the approach of handling ion exchanges like adsorptions? One has to develop this equilibrium curve. Given this nitric acid concentrations, nitrate ions concentrations in water, what is the loading here, Q? So very similar to the isotherm of adsorption, you have also this equilibrium curve where you write down this capacity, milligram per gram for this nitrate ions adsorbed or separated by these reagents. So just the names are different. Fundamental reactions may be different. For adsorption, we say that A brings in contact with S, it's A dot S. Some physisorption, chemisorption, some bond formation is taken place. Here more like it's a chemical reaction, but still you have the similar approach here. In case of adsorption, we took a species balance, differential balance at a distance of x. We wrote down the species in, species out by convections. We write down the similar balance for this ion exchanges. It's only the rate equilibrium which would be different for this from this. At equilibrium here, Q versus nitric acid will follow one isotherms. For adsorption, this is a different isotherms. So although ion exchanges in this course we did discuss, but you should see that it follows the same approach as adsorptions. Your basic thing is that your isotherm is different. You can go through the textbook again by Treball or by Datta. All right, you will see the same approach. So again, we like to conclude today's lecture that we discuss 5 unit operations which are very common in chemical engineering: absorption, extraction, adsorption, drying, and distillations. Last but not the least, the most popular one here. But other unit operations like leaching, solid and liquid, ion exchangers, right? Or we talked about certain more complex problem in the same unit operations. Instead of having 2 products, we have now 3 products. Instead of having 1 feed, we can have 2 feeds. We'll have the same approach. One must develop this very basic fundamentals of mass transfer, starting from equilibrium, rate process, NTU, STU. You can address a wide range of complex problems or different unit operations. So I hope you have enjoyed this course, and I can always be contacted by this or at this email address, nishith@iitk.ac.in. So if you have any doubts, any question, any concern, you can contact me at this email address. Alright, so with this we have completed NPTEL lecture on mass transfer 2. Thank you.